We're going to talk now about equipotential lines, which are just a useful visual device for mapping out an electric potential. Now, it would be useful for us to quickly review topographic maps. If you're a pilot or an avid hiker or a boater, you may very well have read topographic maps before. If not, introducing them to you for the first time, useful thing. Even aside from equipotential lines, topographic maps are a really useful thing to be able to read, just in case you ever have to fly an airplane and don't want to crash into a mountain, or drive a boat and don't want to run aground on a sandbar, or you want to go hiking and you want to, find where the mountain is. So a topographic map is a map of some kind of terrain. So we might have, let's say there's going to be a mountain peak right here. And let's put a lake over here. And we'll have another we'll say it's a somewhat lower peak over here. Whoops, colors. Now the topographic maps are the lines of constant height. What do we mean by constant height? Well, if you take a walk around the lake, you're pretty much staying all at constant height because the lake is level. So there's one topographic line. Now similarly, if you were to take a walk around the peak, okay, not going up or down, but just going in a little circle around the peak, that would also be staying at constant height. So around each peak there's going to be a line of constant height, and there's going to be successive lines of constant height lower and lower as you go down. Now the way I've drawn this peak is a little bit higher than this one, because starting from the lake, you go up 1, 2, 3, 4, 5 lines of constant height before you reach this one. So if each line is, say, 100 feet, then this is 500 feet above. Whereas here you're just going up 1, 2, 3, 4 lines, or 400 feet before you reach that peak. So the extra line means this one's a little higher than that one. This point right here, this is referred to as a gap, or sometimes a gap in the context of talking about mountains or a saddle point otherwise. And what a saddle point or a gap is a point where on two sides you go down, but on the other two sides you're going up. So we can fill this the rest of the way in, and a couple of other things to note. Where we have equipotential lines or topographic lines that are close together, that means a steeper hill or a steeper potential. Going to wind up meaning a stronger electric field. Where they're more spaced out apart, that's where we have flatter plains. To us, a weaker electric field. Now this part along here where the equipotential lines are kind of pointed, that's a ridge. Okay, so if you're standing here, you can go up the mountain a little bit here, you can go down the mountain a little bit, but to either side, it goes down pretty steeply, and that's a ridge. Now the opposite feature is a valley, so here I've kind of drawn a valley, and it's like a valley because you can see if you're standing about here, well, you can go uphill, you can go downhill, but if you look to your left and right, both sides are going up. So when you look left and right and both sides are going up, well, that means that you're in a valley. Here, if you look left and right, both sides are going down. That means you're on a ridge. Of course, the rivers, they usually run down the valley, so here's the little river feeding into our lake. And the treasure, well, the treasure is buried right about here. Now, one other piece of information that topographic lines tell you is the direction of the steepest descent or steepest ascent. So the direction of steepest ascent is basically, if you put a ball down, which way will the ball roll? So if you place a ball right here, which way will it go? Well, it's going to go downhill, and it's going to go perpendicular to the topographic lines. So perpendicular to the topographic lines, that's your direction of steepest descent. And that's going to wind up being analogous to, in our case, electric field. So let's do an example and draw equipotential or topographic lines for a couple of positive point charges. Now remember that the electric potential, or voltage, is related to kq over r is equal to kq over r. So as we get close to these point charges, we get higher and higher potential, but as we move around them, the potential doesn't change. So in this way, they're kind of like peaks. The potential doesn't change as we move around them because R is not changing. We're staying the same distance R from them, so the potential's staying the same, just like if you go in circles around a peak. We can start drawing successive equipotential lines. Now these should look exactly the same, but they don't. But they should be same symmetric situation. Equipotential lines should be perfectly symmetric. And as we get farther and farther away from them, drawing successive equipotential lines, eventually we're going to have to draw an equipotential line that encompasses both. Here then we have what? A saddle point. You go this way, you go down in potential, this way down in potential, but this way or this way you're going up in potential, so this is a saddle point. So here are the electric field lines for this charge configuration, which we learned about last time, and I'm sure I didn't draw it perfectly, but if I got it pretty close, then these are all at right angles to the equipotential lines. Note that the equipotential lines are closer together where the field is strongest, and this corresponds to where the electric field lines are also closer together. And you'll recall from last week that electric field lines are also closer together where the field is strongest. Okay, here in the middle where there's not much field, there's kind of a lot of space here between the equipotential lines. And out here, of course, there's plenty of space because the field is weaker because we're farther away from both charges. Now remember that the definition of voltage says that the change in voltage is equal to the electric field times the change in x. So, times the change in x. So, as the change in x gets smaller, the electric field must get larger. Okay, so just using the definition of voltage, we can sort of get a sense of the electric field, and that it's dependent on the separation between the lines, delta x. As the separation between the lines gets smaller, the electric field gets bigger. We'll do another example, this time of two opposite charges, and we'll get a little bit more precise this time. Let's say that this positive charge is at plus 7 volts, and the negative charge is at plus 0 volts. And let's draw one equipotential line for each volt. So if this circle represents the 0 volt line and this circle represents the 7 volt line, then here's the 1 volt line. Thereabout will be the 2 volt line, 3 volt line around there, 4 volt line looks supposed to look the same as the 3 volt line. There's the 5 volt line, and there's the 6 volt line. Now let's do our electric field lines just to make sure that it's consistent with what we have done with the equipotential lines. And I'm not a perfect artist, of course, but these things, you can kind of tell that they're supposed to be right angles. Some of them are better than others. That one's pretty good over there. And so on, right angle, right angle, right angle. Those ones are easy. Yeah, you get the idea. So, what's happening here? Basically, we have opposite charges, and it's consistently downhill from the positive charge to the negative charge. A positive test charge would just go right from the positive to the negative. And we see that manifested both in the electric field line and in the equipotential lines. Okay, which is going down, 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 down. Contrast this with like charges, where we go down, 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 and then we start going up, 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 up again. Electric field is weak out here, so the electric field lines are far apart, so are the equipotential lines, weak out here, okay, and more strong in between the charges. The previous case we had this kind of void where there's a lot of white space, because the two electric fields from these two charges are kind of canceling each other out. In this case we don't have such a void because these are opposite charges. So the electric fields are actually adding to each other, so it's still pretty strong in the middle here. Let's do a parallel plate capacitor with a voltage difference of 7 volts. We'll call that side 0 volts and that side 7 volts. Of course, I could just call this one 0 and this one -7, it would be exactly the same situation. Equipotential lines, drawing them with a spacing of 1 volt as before. Again, it's pretty uniform, just like it always is between a parallel plate capacitor. Note especially that the spacing between the lines is uniform. That's what tells you that the electric field is uniform, because remember, the electric field is inversely related to the spacing between the lines. We can extend the lines out like this, and now let's do the electric field lines. Uniform electric field, uniform spacing between electric field lines, uniform spacing between equipotential lines. As before, electric field lines kind of bow out a little bit towards the edges of the capacitor, as do the equipotential lines. They start to bow out a little bit towards the edges of the capacitor. Okay, homework problem number 7. Draw equipotential lines for this charge configuration. A plate of uniform positive charge and a small tight little ball of negative charge. 0 volts plus 7 volts. So draw the equipotential lines spaced at 1 volt spacing. Homework problem number 4, same thing. Now for this charge configuration. Now one last thing I want to talk about concerns units. We talked about how the potential energy is equal to the charge times the voltage. And this definition gives voltage a unit of joules per coulomb, also known shorthand as volts. Well, there's another unit for energy, okay, and this unit of energy as opposed to joules is called the electron volt. And 1 electron volt, or EV, is literally just the amount of energy that an electron gains as it passes through a 1 volt potential. So that is just the charge of an electron, or E, times 1 volt. So take the charge of an electron, multiply it by a volt, and that's what an electron volt is. So an electron has a charge of 1.6 times 10 to the minus 19 coulombs. And multiplying that by 1 volt just gives 1.6 times 10 to the minus 19 joules. I just fixed a typo there. I hadn't put the coulomb symbol in there. So that's the conversion between 1 EV and joules. But EV are really convenient because a lot of times you deal with electrons and you want to know what happens if you drop an electron through a 2 volt potential. How much energy does it gain? Well, 2 electron volts. So it's a convenient unit. Let's recap what we learned here. In addition to, of course, this unit stuff above, we learned about equipotential. These are lines of constant potential. They're perpendicular to the E field. This symbol means perpendicular to. Closer together means that it's a stronger E field. And they're like topographic lines in that topographic lines are lines of constant height, while these are lines of constant potential. And this is, of course, related to this metaphor of potential energy and height. Okay, an object tends to roll downhill, and so it rolls across the lines of constant height towards lower height. Well, a positive test charge tends to roll downhill across lines of constant potential. The force on it is perpendicular to them. The closer together the equipotential lines are, the stronger the E field is. Just like the closer together topographic lines are, the steeper the hill is, and the more rapidly something will accelerate down it. So it's really a very useful and accurate metaphor. This connection between height and potential.